So I hope that you still remember that in the last lecture we just derived an equation for what's the bound current. There are bound surface current and bound volume current, right? So it's similar to the bound surface charge and the bound uh, volume charge for this electrical static problem. And here in the magnetic static problem, when we are given a uniformly charged object, uh, we will also produce bound currents. And here, for a uniformly charged objects, the m is a constant, even though it's a vector. So the del cross m, which gives you the bound volume charge, you expect to get that to be 0. So everything should be residing on the surface instead of on the bulk. So now let's try to visualize or try to think about what's the underlying physics behind this surface currents. So remember that somehow because the current here are only supposed to be seen on the surface, so how it appears is something intriguing, right? Because here these currents are bound currents, and you are supposed to see electrons not leaving the core of the atom far away. So they are not ionized, so you don't expect to see one single electron moving out on the surface, right? That is against the idea of a diamagnetic or paramagnetic material. So how this macroscopic current arises is because it's a similar analogy to this polarized material. So actually, because here each electron only finish a very small loop, and now if you combine these loops together, and you see that somehow in the inside, when it's in the bulk, the loop that's on the left and on the right cancel, the current in the middle cancels exactly. And so in the bulk there are no currents at all, and on the edge, because there are no current canceling the current on the edge outside. So in that case, there will be a finite current possible on the edge. So now we can try to see if we can obtain the same thing from from what we get in the last lecture. So we can first get the total magnetization and times the volume, and that gives us the total magnetic dipole. So the total magnetic dipole is the m vector times the volume of this thing. So in principle, this should be vectors, but if I'm talking about the if I'm talking about the magnitude of the vector, they are still equal to each other. And now we can also relate the magnetic dipole moment to this current and the area, right? So this is the definition of this magnetic dipole moment. And now this equating these two equations gives us I is equals to m times t. So here t is this height of this object. So the current on this edge is actually can be obtained by simply multiplying the magnetization vector m and times the height t, and now you can next step is you can calculate the surface current. So the surface current relating to the total current is one length difference. So if you divide by this total I by this length t, then you get the surface current, right? So that's give you back m. So the magnitude of this surface current density is actually directly proportional to magnetization vector m. And now you can also determine the direction of this surface current. So the direction of the surface current should be, if you summing up all these loops, this must be somewhere, something like this. So on the right hand side, you will be expecting current on the edge here, and there will be both currents along the top line and the current along the bottom line, and there are also currents in between. So this is described by a surface current density K, and this K is magnitude is m, and the direction is always within this xy plane. So the direction of the current can be determined by this m vector cross this m vector. So the m vector will be pointing out of the surface here. So then the current direction will be along the direction here. And now from this equation, we can immediately see that the surface here on top, because the surface direction is parallel to this magnetization direction, so the surface on top actually doesn't have any current. Now, if you combine this, then you get that the KB must be equal to m cross n, and this is actually exactly what we obtained in the lecture 15. So here for the bound current, what I mean is that even though it's a microscopic current, however, because the charges actually only moves in a tiny loop, this current is bounded by the atoms, so they are called bound currents. It's a similar concept as the bound charge in polarized materials. Now let's try to see what happens if the magnetization vector is non-uniform. So similar to the case in the polarization vector, so del dot p the bound charge is I believe is negative del dot p, and so here if p is a constant, then the bound charge is volume charge is 0, but here if the p is non-uniform, or if the magnetization vector is non-uniform, then you will be expected to see some bound volume charge or bound volume current. So naively you can think that microscopically here if the magnetization is non-uniform, then it means that here the magnetization vector here is small, but you move slightly along the y-axis, you might get a slightly larger magnetization vector m. And now if you calculate the current here, so for the magnetization vector on the left, the current here should be relatively small, and on the current on the right, it should be relatively larger than the current on the left. So now if you try to calculate the current in the middle. So here, the current on the left and on the right no longer cancels each other, because even though they are in opposite directions, so one is pointing inwards to the screen, another is pointing outwards to the screen. However, the right one is slightly larger magnitude. So these two does not exactly cancels, and that's why there can be a volume current. So now let's try to see if we can get some sense out of the equation for this volume current. Now, how to calculate this volume current? Well, we can use the what's this called, like infinitely small volume analysis. So here we just look at the volume element here and the volume element over here. Now this two volume element has a different magnetization vector m, and also remember that we just talk about how to calculate the current from this page, right? From in this example, the current is the magnetization vector times the height t. So here, for this one, we still have the magnetization vector times the height dz here. That produce current over here. And we are supposed to calculate the current difference between the produced by the left magnetization vector and the right magnetization vector. So the current is in total is here, and now if you look carefully about this equation, when the dy becomes small, this too becomes the slope times the dy, right? So so we can, in the limit where this dy becomes 0, this equation can be abbreviated as the partial mz partial y, the times dy dz. So the next step is, now what I'm calculating here is the current at infinitesimal, crossing an infinitesimal area of dy and dz, right? So here I'm only interested at the current at a really small position here, where y and z is fixed. So this, now we can instead of writing down as a current, total current I, if we divide that by dy and dz, what we get is the current density, right? So the here the J equals to Ix over dy and dz. So if you are unsure about this, you can always go back and check the current density and the current are different by length squared. And because the current is the total current density flux that's crossing one given area, right? So now what we have in the end is the current density along the x direction can be expressed as the partial mz and partial y. Likewise, we can do the same analysis to this current produced by the m along the y direction. So these two problems are identical, except that we switch x, y, z slightly. And if we redo the analysis, what we get in the end will be a similar expression here on the right. Simply change y to z to y and y to z. But here now we have an additional minus sign. And now this one actually looks like a cross product, right? So if you double check and write down the determinant, you can verify that the the cross product here will be identical to this one, except that here I'm only writing down along the x direction, but you can reproduce the calculation along the y and z direction. So in the end, the bound volume current should be equal to del cross m, and that's exactly the same as what we obtained in the lecture 15. So it's the last lecture where most of you have missed. So if you don't know how this comes from, so try to take a look at the lecture 15 recordings. Now here this what we have here is the bound current, and just similar to the bound current to the bound charge, this del cross m actually already also described the physics along the edge. So here this m cross here the surface current seems to have a different formula than the bound volume current, right? So the surface current is m cross n, but this can also be derived from this equation of del cross m. So remember that in the for the bound charge, the rho bound is minus del dot p, and the bound surface charge is written as p dot n, and you mean why there is a minus sign here? I think that's because like how the x, y, z coordinates are rotated. If so from this expression, I think what you can try to deduct is the here the jbx from this equation you might be able to derive that the jb along the y direction should be partial mx partial z, and for this direction, so because this can be obtained by simply shuffling the coordinate system from x by replacing x to y and y to z and z to x, right? But if you look at the coordinate here, this is x, z, y. So the sequence is reversed. So you will be just like the cross product. When you calculate the x cross y, you get z, right? But once you cross x and z, you get a minus y. So that's why there is a minus sign, and this because of this minus sign is consistent with the cross product. But you can always double check by like doing the calculations on the right figure. There should be a minus sign. So here for the bound current, remember that in the previous lectures we said that this equation is somehow can be derived from this equation, and similarly the bound surface charge can be exclusively derived obtained from this equation alone, and in principle if you this equation already summarizes everything about the bound current. So if you take a divergence of this bound surface current, uh, you should get a 0, right? And do you know why that should be 0? Yes, so some of you might already seen the sentence here. So because the del dot del cross m is 0, and so the current is has a conserved law. So whenever there is a current flowing out of the volume, there should be also some other current flowing inside this volume. So the bound current is also a conserved quantity. Okay, so now let me briefly mention that when we are calculating the magnetic fields inside the matter, what we are really calculating is not some magnetic field that's right at the top of atom or at the top of electron, because you will expect that if you measure the magnetic field exactly at the current produced by the electron, you might get something diverge, because consider a linear current, the magnetic field very close to this current can be extremely strong, and so here what we are doing is very similar to what the approach that we use in the electrostatic case. So instead of calculating a field that's fluctuating very large and down depending on the positions of these atoms, what we are doing is average or a smeared out value of the magnetic field. So we don't take account into the exact locations of the atoms, and it's a macroscopic magnetic field. So remember that this actually produce something that this one is responsible for this difference, like when we are calculating the energy stored by a material in electric field. In general, these two are different, and it's responsible because one is calculating the average field, and this is taking account into the internal energy stored by these atoms, and we also could see something similar in the magnetic field here. Now, also similar to the electrostatic case, not only we have a vector called magnetization vector M, and we have a magnetic field, we can also define an auxiliary field H. So in the electric field case, we have the E and the P, and we also define the D vector, right? So here this auxiliary origin of the auxiliary field is similar to the analogy in the electrostatic case. So the first step is what we do is to identify the bound current. Remember that this already give you everything about the bound current, right? And now we simply call that the total current can be separated by to one is the bound current described by the magnetization vector here. Others are free currents. So where does the free current come from? Well, it actually comes from, say, current in a wire, where this wire is powered by a battery or a voltage difference. So these currents are called the free current. And now what we want to do is to derive the Ampere's law for the free current. So we follow the same steps. So now if we calculate the del cross B, that gives us the total current. And because we separate the total current into two contributions, the free and the bound current, and the bound current is del cross M. So now we see that there are two curves, and we can combine these two curves together. And what we result is the equation over here. So what's inside, we can define a new quantity, right? Then we can call this as the H vector. So this H vector is something funny in the sense that somebody calls this also as the magnetic field, and B is also a magnetic field. So you might be confused, like which magnetic field we are talking about. So we now simply call the H as the H field. So so this is something different. Like people call this differently in the literature. That's because like it's very close to like newly discovered physics. So if you are doing research and you actually can see that different people might call the same thing by different names. If you say that if you are doing some research recently, and so different fields can describe the same phenomena by drastically different names. So that's something that you might notice soon if you try to do research. And so if you are reading papers, you have to be extremely careful about identifying what exactly does the author mean. So the same name might apply to different quantities, and different quantities might also share the same name. So also the same name, also the same quantity might be called different things by different people. So be careful. And now if we replace this by H, so then we get is the Ampere's law for the free current. Now if we do the integration on both sides, what we get is on the left hand side we have the if we do integration in an area, and then this area integral on the left can be simplified by the Stokes theorem. So the del cross H can be written down as the H along this loop, and the area on the right can be written as this current flux that's passing through this Amperian loop. So here the JF times the area gives you the current. So it's a current passing through this loop. And now we have the everything for this for this magnetostatic in matter. So not only we have B field, we have the magnetization vector, and we also have the auxiliary field. So this auxiliary field H can have a similar Ampere's law, but you might think that because the Ampere's law for the H field is extremely simple, and this equation is similar to the del cross B equals to magnetic field divided by mu naught, right? So you might think that somehow the H and the B could be similar, but in reality, the H and B are quite different. So remember that for the B field, the divergence is always 0. That's because there is no magnetic monopole. But if you calculate the divergence of the H field, and because B is 0, so the H field is only related to the M, the magnetization vector M. So in reality, this quantity might not always be 0. So what this means that there are no vector potential for the H in general. So for example, if we consider a bar magnet with a permanently uniform magnetization vector, so say that the M is crossing the axis. So in this case, there are no free current, right? But if we find out the magnetic field inside and outside, it's always non-zero, because imagine that this is a magnet. It can attract ions, so there definitely has to be magnetic field outside, and because the outside the M is 0, right? Then the H, it can be related directly proportional to the B. So the H outside is finite for this bar magnet. But if you assume that you can get the H from the del dot, if you try to directly use the equation over here, and say that because the bar magnet doesn't have any free current, and then you assume that H is 0, then that's not correct. So do you know where the del dot M becomes non-zero in this case? So yeah. So imagine at the edge here, and if we take a look at the M across this edge, so inside is finite, outside is 0, and so at that exact edge, the del dot M is not 0. So in general, you can still use Ampere's law to find the H field, and then from the H field you can maybe find out the M and the corresponding the B field, but try not to assume that H is 0 if there are no free current. Okay, so for example, let's take a look at a long copper with a current flowing upwards. So the current is uniformly distributed along this wire, and we try to find out the H field inside and outside this wire or this rod. So this problem has high symmetry because this is quite long, and now for it's a very good approximation that it extends to infinite. So we can simply calculate the H field using the Ampere's law. So you can first calculate what's the H field inside by doing an Amperean loop along this azimuthal direction. So here, in this case, the del cross H equals J free, and now the integral form of this equation is Ch dl equals I enclosed, I free enclosed. So we design an Amperean loop here that's in the xy plane, and then the integral on the left hand side is simply, so here the H field must be along the azimuthal direction according to the symmetry. So here along the azimuthal direction, the length of that ring is 2 pi times s, where s is the radius. And then on the right hand side, the I enclosed is simply the total free current times the total free current density times the area. But the total free current is I, and so the total free current density is I over pi r squared. And now we times the pi s squared to get the total current passing through this Amperean loop. So now inside this wire, we get that I over pi r squared, and there is a Q factor here, and then times s. So the direction for this H is along the azimuthal direction. Now for the current outside this wire, then the Amperean loop is slightly larger, so the H times 2 pi s exactly equal to I. So the H outside equals to I over 2 pi s along the phi direction. So try to be careful that when you determine the direction along the azimuthal direction, the sign here is important. So how to determine the sign? Anyone has an idea? Like, yeah, so you have to use the right hand rule, right? So imagine that you have a current flowing upwards, then the right hand rule can help you decide this direction, that it should be along the plus phi hat direction, and instead of the minus phi hat direction. So so in this question, so the H field is along this phi direction, but if you calculate the M field, it's actually of the opposite direction, and let me see. and the total B field is across the phi direction if you do the calculations. Let me see. So if we take a look at the field produced by, so if we take a look at the boundary conditions of this uh, the H field, we can get something that's simpler or oftentimes more useful than what we have for the boundary conditions on this B field. So the equation below are the boundary conditions that we have derived for this magnetic field without matters or in general case. But now if we put matters into consideration, sometimes it's better to calculate the H field directly. And the H field, so we need to consider the boundary conditions for the H field. So for the del dot H, because del dot B is 0, right? So the del dot H is directly related to the del dot M. And we know that for the B field, the difference crossing a boundary on the perpendicular direction is 0. That's because we derive by using the del dot B equals 0, and we put a Gaussian surface across this boundary. So if you remember, we put a pillbox that's slightly above and slightly below the plane. From this Gaussian integral, we can immediately tell that the B should be continuous along the n hat direction. And similarly for here, for H field is no longer continuous because the del dot M term. So in the perpendicular direction, it's minus M difference. And we also have another direction, another condition that's from the del cross B. We know that this is proportional to this mu naught J, and then we design an Amperian loop. So in this question, we design an Amperian loop that's slightly above and slightly below this plane. So likewise, if we do the exact same thing to the del cross H, because the del cross H is J free, then we simply replace the mu naught J by this J free, and then here the mu naught K becomes the K free. So this derivation is exactly follow the same logic as for the derivation for the B field. So try to see if you can derive the boundary conditions by yourself after class. So now if you try to look back, we have quite a few boundary conditions, right? So we have the boundary conditions for the E field. So we have the boundary conditions for this D, for the boundary condition for the electric E, and we also have the boundary conditions for this scalar potential V. So there are 3 in the electrostatic case, and for the magnetostatic case, we have the boundary condition for B field. We have that for the H field, and finally we also have the vector potential. So there are 6 boundary conditions in total, and I don't expect you to remember exactly but you have to be able to derive. Like if you don't know them in exams, then you're supposed to be able to draw this kind of Gaussian surface, or just this kind of ampere loops to determine the exact boundary condition required. So let's have a visualization of these boundary conditions. So now try to consider bar magnet. So here in this bar magnet, so could you keep quiet? Okay.
Here's a question.
Oh, okay, yeah, sure.
This question is what kind of material produces the magnetization? Feels unclear about how does the magnetization
Compare
come
M and the D. Just like
Yeah, we haven't discussed this yet. So just like the polarization materials, there are two different kinds, at least two different kinds of materials that can produce magnetization. So one is permanently magnetized object. So there's a ferromagnet, right? So a ferromagnet has the magnetization retained, even there is no leftover magnetic field. And this is similar to the permanently polarized materials or the frozen polarized materials. And actually, the ferromagnets are more frequently seen in daily life, right? But there are also a different kind called the para or diamagnetic. And these we will talk about later. That these are called linear media. That the magnetization vector is simply proportional to the B field, or you can think of this proportional to the H field. And we will discuss this later, but today we just say that claim the material is magnetized, and to see what happens. Okay. Any other questions? So now if we take a look at the boundary condition, say for this bar magnet, so the bar magnet is simply a permanently magnetized object. So you can think of this is the north pole, this is the south pole, and it's magnetized. And now if we calculate the field that's outside of this we might have not calculated the exact case of this problem, but we calculate a similar case. I believe it's uniformly polarized shell, but here it's similar that outside this object, the field is similar to a dipole if this bar is thin enough. So so you can imagine that there are. So I think this should be the south pole, right? This should be the north pole. So the magnetic field flows outwards from the north pole to the south pole, and it's like it makes a loop. But remember that here at the edge there are also magnetic fields. And the H field outside is very similar to this to the B field, because here let's check. Here H equals to B minus M, so so outside, because this M vector is 0, So it should be identical to the B field outside. And now inside, because the magnetization vector M, uh, there is a so the B field inside should be subtracted with magnetization vector M vector, and this M vector is actually the vector that produces B, and if you calculate that the B produced by the M vector should be smaller than M itself, so inside the H field is actually along a different direction than the B field. So the B field inside is pointing from north pole to the south pole, and but inside for the B field it's pointing from the south pole to the north pole. So the magnetic field here is continuous along this edge, but the H field is not continuous. So try to remember that that's because del dot B is 0, and the del dot H is no longer 0, and what's the discontinuity is exactly determined by this M vector. So here, if we check back, this discontinuity is the discontinuity defined by this M vector, because the M is 0 at inside and non-zero outside, so this is finite. And try to think about if you can verify all these boundary conditions by this bar magnet. And this is the lecture today. So we will finish the chapter 6 in the next lecture, and we will also start discussing chapter 7. So you already have everything that's required to do the homeworks of chapter 6, and please also submit your homework today for chapter 5. Okay, yeah, thank you.